Okay. Once again, good afternoon, students. Today, our session is on fluid mechanics, and when we talk about fluid mechanics, so normally there are two parts. One, we want to discuss about the fluid at rest, and another one that we'll discuss in our second class. So that will be fluid on motion, means some moving fluids, and that is the second topic. But today's topic is fluid at rest, and here we will see what are the laws of those fluid at rest, and what are the formulas, and what we can do, and what is the purpose of studying this one. So time to time, I will take a pause and I'll show you some demonstration, some live videos that will help us to understand. So please feel free to stop me at any point, at any time, and ask questions. I don't mind if you interrupt in between, even if I'm not finished with my sentence, but please, you interrupt, because it is the 1 hour session, and we want to effectively utilize this 1 hour session for the best of your time. So now, matter, we know the matter are basically in three states: solid, liquid, and gas. So that is very known and common states of matter. Apart from that, there are few more states are there, plasma states and other states are there. Some of the books you will find semi-solid, semi-liquid, those things are there. So we are not going into that granular difference, or whether it is solid or liquid or gas or semi-gases or something like that. Broadly, we understand what is solid, we see what is liquid, and we also see, we know, we cannot see the gas, but we know what is gas. So what is the difference from a science point of view, from our scientific understanding point of view? What are the differences of solid, liquid, and gas? The main differences is that intermolecular forces are strong. Means if I take a solid, so for a solid object, for any object, let's say it is a, it's a ice. Ice is the best example. So ice, if we heat it, it will be water, and if we more heat it, it will be vaporized, and that will be a gaseous state. So now in case of ice, so that is the good example we can take, and we can discuss on that. So their intermolecular forces are strong compared to liquid. When we say the strong, always we have to measure or compare. Unless until we put a mathematical expression, that statement doesn't complete. So strong compared to the intermolecular forces of liquid, and when it goes to the gas, it is very, very less. So this is all about our understanding, of very broad understanding. So slowly I am moving from very common understanding to the scientific analysis and scientific knowledge on that particular topic. Here, what we see, the mass and volume relationship. So this is very important concept here, and we all know that it is nothing new to us. But once again, I want to reiterate on this basic formula. For any scenario, the mass, the amount of matter within that particular liquid, solid, or gas, whatever it is, the mass equal to the volume and the density of that particular material, whether it's a solid, liquid, or gas, doesn't matter. So mass equal to volume into density rho. So here we are denoting density as rho. Moving on, now as today's topic is on the liquid. So now where from this liquid comes, so that is the basic understanding. That is the state of matter coming from the solid, liquid, and then the gaseous state. So today's understanding or our discussion will be based on the liquid, and that too liquid at rest. Please remember this thing, liquid at rest. We are not discussing the liquid on motion. We are not discussing the liquid is flowing or liquid is moving inside a tube or inside a tunnel, or is not like that. So our topic is liquid at rest. So now when we discuss about the liquid at rest, two things very important here. That liquid should be incompressible. Means here again I'll just spend a couple of minutes to understand these two statements. Without these two quality of the liquid, those formulas will not hold good. Here the density of the liquid cannot be changed. The more pressure we put on the liquid, the density will remain constant. Means if we compress the liquid, if we put say piston inside a tube, and if we just put the pressure from both the sides of the liquid, maybe due to the pressure the liquid can leak, or the piston may burst, or something may happen, but the volume, or the volume will be squeezed, but the density cannot be changed. So that is one property of the liquid we are dealing with here in our this discussion. And another thing, non-viscous. So that is also an important concept. Non-viscous means we are dealing with certain liquids that do not exert any tangential force. See, I just wanted to show you on the camera, but unfortunately this setup is not there. Sorry for that, but in the next class I'll make sure it is there. So what I am saying, or what I am trying to make a point here, we have that liquid flowing. If you can follow the camera, so here liquid is flowing. Now there is a layers of liquid flowing, or in a object it is still, but my assumption is here in this liquid class that one liquid layer and another liquid layer, they are putting pressure from the top layer is putting pressure on the bottom layer, and so on. It will go to the bottom, and it will come to the bottom of that particular beaker or particular pot, but there is no tangential force. There is no, the perpendicular force will be there, but there is no tangential force between two layers of the liquid. So this is very important concept. We will see the viscosity and the surface tension, all those things are coming. But when we are considering the liquid at rest, we will consider that there is no friction between the layers of the liquid, or among the layers of the liquid. So non-viscous liquid and liquid density cannot be changed. These are the two important things. Please remember. But I'll come to this point once again. Now, coming to the concept of say thrust, force, and pressure. We all know that what is force to some extent, or we have seen in our Newtonian physics or Newton's law of motion that what is the force and what is thrust. Now, here another concept we'll try to understand, we'll discuss, and please stop me whenever you see that okay, something you are not able to understand. We are talking about the pressure. So pressure is the force applied on a particular area. And how do we measure the pressure? It is, if we denote P as the pressure and F as a force, it will be F by A. F divided by the area will be the pressure. So thrust is defined as the force acting on a body perpendicular to its surface. So now the force acting on a body perpendicular to the surface means it is directly making a 90-degree angle to that surface. Now, if I put a force, something at certain angle, theta, with that perpendicular distance, then I have to make the perpendicular component of the force. And of course, if theta is the angle and F is the tangential force, or the force making an angle theta with the perpendicular distance, so F cos theta will be the perpendicular component. And if my area is A, then the pressure will be F cos theta by A. So lot of mathematical problem will be there on this concept. So I just tell you to read the book here and to get that understanding. If some pressure is coming at certain angle, and I need to derive that perpendicular component of the pressure. Yeah, any question, anybody, please feel free to stop me and ask question. Okay, so now pressure has some unit. As we know that everything, every measurement should have a unit. without that, that measurement will not be complete. If I say just a number, so number will not give any idea about that unit. So we know the pressure equal to force by area. Now force unit we know it is Newton, and area is meter square if the length is measured in meter. Then unit of the force Newton meter to the power minus 2 or Newton by meter square. And now it is denoted as Pascal. Pascal is a great scientist who has Pascal theory and a lot of other invention by Pascal. So in name of the honor of that great scientist, we denote Pascal 1 PA, 1 Pascal of pressure equals to 1 Newton per meter square. Please remember this. This is a so don't denote pressure as Newton. So it will look something funny. See, I sometimes I give an example. If somebody asks me for how many hours did you for how long did you sleep? If I tell okay I slept for 7 kg or slept for 5 kg, it sounds funny. We do not understand anything that okay I slept for 5 kg. So same way, if you tell that by pressure is 1 Newton, that will also sound funny to a scientific person, to a scientist, or to a physicist, or to a person who understand what is pressure or what is force. So always put the pressure unit as Pascal or Newton per meter square. So remember this thing, the pressure equal to force by area. Now we talk lot about this force, pressure, and this thing. Now quickly I just want to show you one one short video on this topic, where I'll just demonstrate about what do I mean by what I am telling, and what do I mean by this pressure, how does it look like. And I'll just quickly show you about, maybe I'll go to the next one. So here there is a small video, so I'll just try to show you the small video to give an understanding of what is mean by pressure, what is mean by the pressure, and what is mean by the force. So now, Ujjwal sir, are you able to see my video, or a student, are you able to see the video?
Yes, I'm able to see it.
Okay.
Yes, sir.
Okay, thank you. Here I'll just come to the exact point. Now you see this is an amazing video, and this is from a scientific video. It is not a magic or anything. So now what we are going to demonstrate, there is a nail bed. I'll just pause the video here. You see this bed is made of nail, and you know that this nail is perpendicular, means it will get the entire pressure, whoever or whatever putting on the surface, that will get the entire pressure. So now what I am trying to show by showing this video, now you see, if you stand on this nail, then that nail will be passed through your legs or your hand, whatever you put, but one man will be laid down on the surface of that nail, and after that one hammer will be just crashing the bricks, that you know the brick we make, you use that brick to make our buildings, and that is a cement brick, hollow cement brick. So that will be crashed using a hammer, and how it can withstand that kind of force. So nothing will happen to this person. So I'll just, for the sake of our understanding, I'm just moving this video a bit, and then you can see that. So now just for few minutes, just observe. And what I'm trying to make a point here, if you stand on this nail, you see the nail, and you see what this guy is doing, and it is not a magic. My main point here, from a scientific eye, I want all of you to see from a scientific eye, from a scientific understanding. It's not a magic, first of all. It is the law of force and pressure, how the pressure varies if I spread the area. You remember P equal to F by A. Now you see that this guy, what he is doing, it is scary. It is scary, but it is not. It is not, because you see these they are from a UK college, and they are not showing some magic or not doing any fun. They are also trying to explain the pressure is less if my area is more. That is the important concept. Please try to remember that. P equal to F by A. If I increase my A is at the denominator. If I make the A more and more, my pressure will be less and less. So that is the main concept. My force is coming as a thrust, means the perpendicular force. You see the hammer is directly straight to the nail. But you see, so this guy, he got some thrust. Of course he got some thrust, but as the area is more, area is very large, and nothing will happen. You see, you'll see some nails dot. If you see very carefully the jacket, if you see very carefully the jacket, when he opens the jacket, and here if you see some the dot, like the dot on the cheese, but nothing happens. So the main point here, that P equal to F by A. Remember this thing, P equal to F by A. Memorize this thing so that you don't have to read that one. What I am saying, what you see on the demonstration, just remember that part. Now, I'll just move back to our slide. So any question or any thought, any idea what we have shown in the demo? Any idea before I move on to the next slide? So this is the nail bed, and you see the amount of pressure. Hammer, one full force hammer is coming with a strong force, but the pressure is getting minimized as the area is more. Area is more. If you think that if you sit on this nail and if you put somebody on the hammer, then of course that nail will create some problem and it will damage your body. But here it is not happening, and I am making that area more. P equal to F by A, and therefore the pressure is coming less as A is large. I hope it is clear to all of you, student. If any comment, any thought, any ideas?
Fine. You can proceed.
Okay. Thank you, sir. Here now I am coming to. So why I put that as an idea that this is the pressure of a solid object. Now coming to pressure of the liquid. Remember our topic is liquid at rest and how we deal with those formulas and what are the understanding. Now we know P equal to F by A, as you see on the screen here. F equal to force, and in this beaker we put some fluid, and the height of this fluid here is H. So that is the height or depth of the fluid in the containing in a beaker. Now the force, this is very fundamental, nothing very high, but slowly we are going deep and deep into this analysis. So the force will be here, if we just ignore the force of our atmosphere force for the time being, the force here is just the weight of this particular liquid in that container, and this liquid container is filled with some depth H. Now if m is the mass of that liquid, then of course that due to that gravitational acceleration, mg will be its weight. We all know that. Now if mg is that weight, so F equals to mg, that we know that. Now we want to derive little more, as we have seen in the first slide. M equals to nothing but volume into density. V multiplied by rho is the density. So some of the book you will see that they consider as a cylindrical cylinder of that particular liquid column, imaginary cylinder they are taking, filled up with a liquid. Now how do you get the volume of the cylinder? In the book, of course, you should read the book, but just get that concept here in this session right now, so that when you read the book, it will be very easy to you, and your study will be done here itself. And when you read, then you will be ready for do the practice state in our Ponar classes. All those questionnaire you can do it immediately. So volume into density. So volume means it is area into height. We all know that if you take a cylinder, or if any cube or cuboid or cylinder, anything, so it goes with area into height, and density remains with that mass. So this is the mass. Now if you put the value of m here, so it comes to a h rho into g. G is constant on that place. Now pressure is coming, force by area, we all know that, we have seen that also. Now this area and area, if we just do this mathematics, it is coming to h rho g. It is very simple. The important point what I am trying to make here, we have seen just now in the video, for a solid pressure, area playing a major role. If I make that area more and more, my pressure is getting less. But what happens in case of liquid? There is no role of area. The liquid pressure at this point, or if you combine all the points at the same depth, the liquid pressure will remain same. So what is the conclusion here? I'll come to this slide later. What is the conclusion here? The pressure equals to the height of the liquid column, the density of the liquid, and the acceleration due to the gravity at that place. If I take that liquid at different places, the gravity differs. Or if I take the liquid at moon, the moon gravity is 1/6 of the earth, so that will be less. But my area is nowhere coming into play. Area is nowhere coming into play. It is h, rho, and the gravitational, that acceleration. Now the main point to remember, if you see this one, and this is a very common example you will see in our books also, that if you put a hole at the bottom, so the amount of liquid going this way means it has more pressure, but if you go upwards, means the depth upwards, means the depth is coming less, so it has less pressure. At the top it has the lowest pressure. So we all know that, though
Hello? Hello? Just give me a couple of minutes, I think. Um, there is a issue in the... Yeah. Just give me a couple of minutes.
oh, I'm sorry, I somehow it got on mute. Are you able to hear me now?
Yes. And now I'm able to hear you. Yep.
Very sorry, very sorry. Please pardon me.
No, that's fine. That's fine. No problem. Go ahead.
I am sharing my screen. I'm not sure where I got disconnected.
You need to share the presentation.
Yes.
Yeah.
Okay. So this is the point, that liquid pressure doesn't depend on the area. it depends on the depth of the liquid, the density of the liquid, and the gravitational acceleration, or the small g, what we call that of that particular place. So this is the conclusion for that. Now, any question from anyone? Okay, so I am proceeding. If you have any question, please feel free to stop, and then if every one or another law will try to see the video, and will try to understand how these things are getting demonstrated on real life, and how we can measure it. Unless until we measure or we put in a mathematical equation, it has no meaning, or it has no sense. We cannot use it. So therefore, I'll just take help of the video and will show you. Now, coming to one important concept of Boyle's law. So here, what we see here, we plot a volume. Of course, here we are dealing with the liquid and the gas. Boyle's law applies on both the cases. And in the graph, it shows the volume decreases. Volume decreases if pressure increases, and volume increases. If you see, volume increases here, but pressure is very less. So that graph comes like that, means the multiplication of pressure and the volume is constant. So that is the very simple and the very fundamental law. And using this law, you will see a lot of questions are coming, and a lot of problems you can solve it using this law. So just remember this law. It's a very simple and easy law. P on V1 equals to P2 V2. Means the pressure and the volume at initial state, and the pressure and the volume at the final state are same. Of course, the temperature needs to be constant. So that is the assumption, the temperature will be constant. And then we'll see that P on V1 equals to P2 V2. So instead of talking much more, if we see some small clips, video clips, again, here we'll see that how we can derive this one. So it's a small tube. I'll just explain what this guy is doing. And again, this person is also from another university, and he has put some liquid here in a small tube, and top portion is vacuum, means it contains some gas of this particular liquid or some air. And now, as he press this particular point, the liquid will, of course, the liquid will flow, and the volume will be contracted. Yeah, any question from anybody? I just hear some voice. If you have any question, please feel free to stop me. So I'll just quickly go to the video here, how this person is demonstrating Boyle's law here. And we'll just come to the point. This video has a long demonstration, so we'll just come to the point how he is measuring and plotting those things. Now he is tightening this particular tube, where it has the bottom portion is a liquid, and the top of that particular liquid is empty, where it is filled up with gas. And now the more, let me make it full screen so that, see, so the moment he press, it will, of course, the liquid will go, and the volume of the gas here, the volume of the gas on the top portion, it is getting contracted. So now the Boyle's law says that pressure and volume multiplied, the pressure and volume equal to constant, and therefore we see that graph. The graph is, remember that graph, and how this person is doing this one with a very simple equipment. You can do it at home also. You can do it at home. So he has some equal weight and equal size of some books, as you see on the right hand side, and he will put those books one by one, and one book means that x-axis 1 point, and then he will measure that particular volume. As this area is constant, he will just measure the particular volume by a scale, simple or centimeter, millimeter, inch scale, what we use, 6 inch scale, and he will measure. So the more number of books he puts, then of course that liquid will flow more towards that small tube, and the volume will be less, and therefore he will just take the reading and he will plot it, and he will get that exactly same what Boyle's law tells us, and we'll see that exactly the same graph is coming. So if you see the measurement carefully, and this particular presentation will be shared, so you can check that. So now is plotting. That person is putting say one book, then one dot on x-axis, and measuring the length and putting that on the y-axis and getting all those points. You'll quickly see that, and we are getting exactly what Boyle said, Boyle's law. So this is the proof of the Boyle's law. You can also do it at home. So why I am telling and why I am see, book, it is written, it is already there in the book. We all know that. But this experiment, you can do it at home at your leisure time, free time. You can see that. And the moment you see that experiment or moment you do that experiment, it will be memorized forever in your brain. See, remember one thing. This 1 hour, what we are using, that should be effectively utilized, and that should get into your brain and mind so that you never forget that. Okay, so this is the whole idea of telling and showing that. So they are just plotting that number, and 1, 2, 3, 4, 5 books this person will put, and you will see that what is happening on the graph. And if you just join the dots, you'll see exactly the graph what I have shown you, that is actually Boyle's law, and we'll see that. So now you see 85 of those points are they are putting, and you see on the right hand side here, they're plotting on the board on the right hand side. They're taking the reading and the plotting on the board. And again, it is not just for the fun, so it has some understanding, a deep understanding. Now you see that those plots, how it is coming. 1, 2, 3, 4, 5 books, 5 books, and the more pressure they put, you see the way those length is coming. So you can see that video, but the main point what I'm trying to make here, the P and V, P multiplied V is constant, and therefore we get this graph. And if you take any point and take x-axis, y-axis and multiply, and then you'll see that it is constant. If pressure increases, volume will be less. If pressure decreases, volume will be more. Another example I just want to give here. Maybe you can see on that. So you have seen that. Now I'll just go back to our main discussion here. Any questions or anything? So if you see this Boyle's law, so another example I can give on this context, where you can see the aquarium. Aquarium at the bottom we have some air bubble. We put some oxygen or something to keep our fishes alive in the aquarium. The bubble, when the bubble comes up from the bottom to the top of the surface of that water, so it bursts and it increases. So from the bottom it is less, it is a small circle, small sphere actually, small sphere, and then on the surface it will be big, and at the top of the surface it bursts. So means the pressure, we know that P equal to H rho G. So H is less on the top, and there it has less pressure and maximum volume. Maximum volume means the sphere will be more and more, and it will be burst. So that is the Boyle's law. Any questions, anything, please feel free to stop me, because some important concepts or some important laws of fluid at rest we are discussing here. We are trying to understand the concept and make sure this concept gets into your mind, because these are the proven laws, proven facts, and those videos, those understandings, this discussion will help you to make it ready for that subject, so that this, again and again I am saying, so this time gets effectively utilized here. Okay. Now, going to another concept of Pascal law. So, what Pascal said. See, the statement, the writing, what is here, that is already there in the book also, and you can also read the same thing. And I have also copied from the book, because this Pascal told about the Pascal law and what it says. Try to understand that. And on the right hand side, you see the picture, and we have all observed to some extent in our car servicing, so that very heavy car, you take the car in the service station, the very heavy car, immediately they put on some plate, and this car will be lifted, and by pressing a switch they do that. What happens exactly? Immediately they do that. You do not need, you can do it also. So you do not need, say, a crane or a very heavy equipment to lift that car. And this is exactly what Pascal said on his law, and based on the Pascal law we are doing this particular activity. And here Pascal is saying the amount of force you apply in the liquid, amount of, and that force, that pressure, that force will be converted into the pressure. We know that P equal to F by A. So that pressure will be transmitted throughout the liquid, at every point, without losing its value. So I'm just telling in a very simple and easy way to understand. Of course, in the exam, you need to tell that exactly what Pascal has written in quote unquote, that if the pressure in a liquid is changed at a particular point, the change is transmitted to the entire liquid in all directions to every other point without being diminished in magnitude. Means, if I put a small pressure, very little pressure, if you put, so that pressure will be transmitted throughout all the points of the liquid without losing any pressure, and it will be applied to all the points. So that is what Pascal is saying. Whether you put the pressure, whether you release the pressure. So the Pascal law is saying the change, the change is transmitted to the entire liquid in all directions. The change of pressure is transmitted. So if you put the pressure, the excess pressure will be transmitted. If you release the pressure, the car will come down. Means the pressure will be also released from all the points. So this is the Pascal law. Now, what we see here, we know that here P equals to, here if I put F1 force, remember we are putting force here, and area is A1. This cylinder area is small. Right side on the B cylinder is area is much more bigger. This bigger area is A2. So now if you put F1 force here, the pressure will be F1 by A1. We all know that. Now this F1 by A1 will be coming throughout the liquid at every point without losing its value. Means all the places it will be F1 by A1. That is what Pascal said, and that is what is proven, and that is what has been established. Pascal said few hundreds years back, but now that law holds good in today's age also, because it is proven, and that is the proof I am trying to explain. Here, F1 by A1 pressure is transmitted through this liquid without losing its value. Means it will be always F1 by A1 all the places. So means at point B also it will be F1 by A1 for sure, because that is what Pascal's law is, and this is the fact is. Now if the pressure here is F1 by A1, then what will be the force? If we consider force as F2, so F2 equals to, I'll just go back just to memorize you. I'm sorry, I cannot do the board work. From the next class, I'll do the board work. So P equals to here F1 by A1. We have seen that pressure equals to force by area. Now F equals to P into A. But here my value of P is coming. Here my value of P is coming F1 by A1. So F1 by A1 multiplied by area in this case. See, F1 by A1 is coming here also, as Pascal said already. Pascal's law has been said. Now here F1 by A1 into A2 will be the force on this column. So now what we get? F2 equals to F1 by A1 into A2. So A2 area, if you make large and large this A2, F2 will be more and more. It's a simple fact. Then the force F2 will be much more, so that it can lift any heavy weight, any heavy object, whether it's a car or anything. It can lift a heavy object, and that is what exactly we are doing in our day-to-day life. In the next video, we'll see that how the Pascal law is applied in our modern life today. What he has said, say a few hundreds years back. So pressure is coming F1 by A1, same pressure is getting transmitted without losing its magnitude, and the force is coming F1 by A1 into A2. That is the force is coming, F2 force is coming. The more the area, larger the force F2. Or you can less that area A1, larger the force will be F2. Or you can put more F1, of course it will be F2 will be more. So this is the way we can manipulate the area and we can make that vehicle lifted. Yeah, any question or anything? Ujjwal sir, are you able to hear me?
Yeah, able to hear you very clearly. Go ahead, it's fine.
Okay. So maybe I can take, say, though it was 1 hour, maybe I can take, say, 10-15 minutes more. So I hope it is okay for that.
Yeah, sure. Go ahead.
Okay, thank you. So important concept. So so students, hope you are not getting bored. If you get bored, let me know. So, and don't just listen what I say or what is written there. Question it. Try to understand. And here itself, your study will be ready. Your entire chapter of fluid mechanics, fluid at rest. Another chapter will be there, fluid at motion. So that will be discussed later. But this will be ready here itself. So you don't have to do too much of effort. So here what we are going to see, how Pascal law in today's date it is relevant and how effectively it is getting utilized here. So I'll just, so now okay, another thing here. So just see the video. So you have seen in Bangalore, in Kolkata, in all the cities they are making big roads, and this kind of hydraulic mechanism they are using. So here also, as I told, so they are also using and lifting a car. So what I said, this is just a more small video clips, nothing more. So this is the use of Pascal law. So when you see on the road next time, when you go to a car, when you see that, when you go to the service, remember the Pascal law. So that way, if you remember, you'll never forget what we are studying here, and on real life what we are seeing. And that is exactly what I am trying to make a point here, that you see this car is lifted, F2 equals to F1 by A1 into A2. So you'll remember this formula when you see the car next time. So that means it is getting into your mind and brain, and when you get some problem on this particular topic, I think it will be very easy for you to understand and solve those problems. And those problems and all those things all are coming from theory. If you understand the theory better, you can better solve the problem with that mathematical equation. Of course, you need to remember the mathematical equation. So these mathematics you need to remember. You just not remember, okay, I have seen this car is lifted, then what is exactly happening? Exactly happening means the force F2 is acting. What is F2? F1 by A1 into A2. So what is F1? Other side, some small force I am giving, because I have to put this on a small area. So therefore, I am getting more force. So this is the way you can remember. When you see the nature around you, you will understand easily what is happening. So this is all about Pascal law. Another important thing, hydraulic brake. So this is there in your book also. And I'll just try to explain very easy and quick way. So please stop and feel free to ask questions. Again and again, I am asking. The more you ask, hope I am clear your understanding. The more you ask, better will be your understanding. I don't mind if you ask very basic questions, silly questions, wrong questions. All questions have a meaning to me, and you can ask any questions anytime. Please feel free to stop me. Another important thing I am telling you. Now, we have seen that pressure is coming, force is coming, entire stuff is coming. As I see the video, this point comes in my mind. They are squeezing the ball, and this pressure is coming in all the direction. Can you tell me the pressure is a scalar or vector? Scalar or vector? So we have two things. Yeah, tell me
Scalar, sir.
Scalar. Scalar.
why it is scalar.
Scalar, sir.
Thank you. Right answer. But why it is scalar? Why? Pascal said or I said?
Because it can
Is it what of that?
It has only
me.
magnitude.
But it has direction too. It is going in a different direction. If you squeeze the ball, or if you see see, it has a direction. Na? It is going in this direction, this direction, this direction. Isn't it? See? Why? Again, I am asking, please don't mind. I am asking to make your understanding clear, not to show you that, okay, this is not that answer. Let me tell you. See, it is a scalar. Very right. Why it is scalar? Because its direction varies from one end to other end. See, this pressure is coming from here and it is flowing along with the liquid and it is hitting all the point. And it doesn't go by the law of vector. Vectorian algebra, it needs to satisfy. Then only I'll call it is a vector quantity. Let me give you another example here. Current. We have seen that current is flowing. Current is flowing through where? We know that. Student, please help me to make it interactive. So current is scalar or vector? Tell me. Current has a direction, right? The way you said scalar, very good. See, it has a direction too, but that direction is a meaningless direction. If you rotate the tube this way, that exactly we'll see in that our hydraulic brake. See, if you put this way, so it will rotate. It doesn't follow the law of Vectorian algebra. Vector has Vectorian algebra. We all have learned that. Maybe I can take a small class on vector, not this long class, long discussion. So there it needs to satisfy the law of Vectorian algebra, that this vector, then resultant vector will be this direction. Here, pressure and current never obey that Vectorian algebra. You see, you are putting the pressure here, it is coming there, it is going in a tube, and it is going to this piston, that piston, again it is going this direction, that direction, and so on. It is going in all the direction. It has no perfect direction and it doesn't obey the vector law, and therefore it is a scalar. Same applies for electric current. Electric current is purely a scalar, though it has a direction, though pressure has a direction. Pressure has a direction, but meaningless direction. It goes all the way. In this example, what you see here, if you put a hole here, it will go this direction too. If you put a hole here, it will go this direction. If you put a hole in the bottom, it will go bottom direction. Meaningless direction, directionless. So it has a direction, but it doesn't obey the vector algebra, and therefore it is a scalar. Student, it is clear?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you. Okay, now coming to hydraulic brake. See what happens. You put the brake when you are driving, or you have seen in a big truck, they're putting the brake paddle. Brake paddle is there, so steering is here, and the person is sitting maybe some chair here, and brake paddle is not closer to the wheel because we know that wheel is touching the road. But I need to do something, some lever or some mechanism, so that I can put some pressure on the say brake shoe, so that it helps me to stop the car. Okay, so this is a mechanism, this is a mechanical arrangement, and the more you study, you will know that how those levers and etc there. So that is not our discussion now. Our main discussion is this paddle is putting some pressure. Same way the pressure was given here, so same way, but here we did some arrangement so that the paddle is near to the driver and near to the steering, because he can see the road and at the same time he can put the brake. But brake should apply on the wheel. Brake should not apply on the brake pedal. That pressure is transmitting here, and it will also follow the Pascal law. Okay. Now that pressure is coming here, and as Pascal said, as Pascal law is saying that equal amount of pressure is also flowing from this tube, this tube, this tube, this tube to this tube. Also, it is going to other side of the wheel. So we are considering for our understanding one wheel. So this pressure is coming here. And remember, this magnitude is not getting less or more. Same magnitude is coming. Means when I put the brake, the same pressure goes to this wheel and all other 3 wheels. Total four wheels also get that same pressure. Otherwise, if you put the brake, it will skid, or it can make some accident. So now this pressure is coming here, and the same pressure is also going there. That is exactly the Pascal law is. Now this pressure is coming here. What is happening? If you understand one wheel, other wheel also same thing will happen, because same pressure is going to all the 4 wheels. So what is happening in the one wheel? This pressure is coming. Okay. Now this pressure is coming here inside this cylinder, and we have kept 2 piston or multiple piston depending on the design of the car, depending on the variety of the car. Maybe in the auto you may see one say small piston, in the truck you'll see big piston in the big car. So I'm just for your understanding telling you that doesn't matter that what the piston is and how the piston is. The main point here is the brake paddle is putting the pressure here, and that pressure is getting transmitted throughout that liquid, and that pressure is coming here and forcing the piston to act on the outside direction. So I am putting the pressure here, that this piston is putting the pressure on this liquid. So this is called a brake liquid, and here this brake liquid is also there, and this is also putting the outside pressure. This piston will expand, it will put that outside pressure, and the outside pressure will be there in this inside rim of the wheel. There is brake shoe is there, and it will try to stop that rotation of that wheel, and therefore this pressure is helping us to act as a brake. So this is a simple hydraulic brake, and this is also used in today's car as well. Though we have some electrical brake and other things, I'm not coming to that discussion now. But hydraulic brake is also very much popular in today's vehicles. Also, it is used, and it is also based on the Pascal law. Any question in understanding? Though this diagram looks something very tough or critical, but as long as my Pascal law is concerned, my understanding of this pressure is concerned, remember this pressure is coming through this brake paddle to this piston. This pressure is coming to the fluid. The moment it comes in the fluid, same pressure will be transmitted to all throughout the fluid, and that pressure again, it will be applied to the inner piston, and that will be expanded, and that will also put outer pressure on that brake shoe, and it will put that on that inside rim, and it will try to break that particular wheel. Is it clear? Any question or anything to understand this? Yeah, sorry. Somebody said I cannot see your name. My screen is full mode. So next time I'll try to put 2 screens, and I'll make it much more interactive. But somebody said something. Please tell me if you have any question or any comment or anything.
Yeah, fine. You go ahead.
Okay. So this is now the last. So we are coming to the last. I'm sorry for taking time. Ujjwal sir, will you allow me 10 more minutes?
Yeah. Go ahead. No problem.
Okay. Archimedes principle. See what we have seen: Boyle's law, Pascal's law, then Archimedes. We all know that story of Archimedes, right? That king told Archimedes, "In my crown, can you find how much the real gold is there, or real material is there, and how much that impurities are there?" You know that story, Archimedes, right? I am not getting into that story right now, but the main essence where from this particular Archimedes principle is coming. Why I am telling that story, so that you can relate it, what happens and how he came to this point. So here now again, fluid at rest. I just highlighted this point. The fluid at rest. Archimedes principle will also hold good at fluid at motion, but we need to consider viscosity, surface tension, and all those other components. But here, what Archimedes principle at your syllabus, at your subject is there, fluid at rest. Okay, so Archimedes principle states that when a body is partially or fully dipped into a fluid at rest, the fluid exerts an upward buoyant force equal to the weight of the displaced fluid. It is very easy, though the statement says a very long statement. See what it does. Let's say this is again, this is filled of a liquid, and this is a object, this is a ball we are dipping into the liquid. And you have seen that if we take a bucket of water, and if we take a plastic ball, and if we try to force the ball to put inside the liquid, we see upward force. And that is exactly what Archimedes said. Archimedes went one step ahead and given that mathematical expression, and that is very much required also in our exam or in our understanding. Unless until there is a mathematical expression, it is very, very difficult to make other understand and make for ourselves also. So Archimedes is going one step ahead, telling that weight of that displaced fluid is equal to the force. So the force is equal to weight of the displaced liquid. So the displaced liquid, if we consider displaced liquid weight as mg, so Archimedes is saying, so I'm just trying for that formula, what it is. Yeah. So buoyant force B equal to mg. So B is the buoyant force, and it will be the weight of the displaced fluid. So if m is the mass of that fluid, and we know that g, small g, is our due to our gravity, so the weight of that displaced liquid will be the buoyant force. So that is what Archimedes law is all about. So it is nothing to worry about too many sentences, but try to remember this way. See, I am dipping any object inside any liquid, whether it's a water, oil, or any other liquid. Now it will experience a force, upward force. It will experience the upward force. See, it will also experience a side force. The side force that is there, that will cancel each other, but resultant force will be there upward. So upward force is equal to the weight of the displaced fluid. Means, see, I am putting a ball here inside the liquid. If you see my mouse pointer, if you see this particular, this is a very simple diagram, and lot of examples are there. So now same amount of fluid will be displaced. Just try to understand this. This is a ball. Now if I dip that ball into the water, the amount of water will be displaced by the ball because of its volume, because it will occupy some space, right? It will occupy some space inside that liquid, and then where from it will get, because it has to replace that amount of volume of water from that particular area or that particular volume. So here the amount of liquid it is throwing out from that particular bucket is equal to the force applied to that particular object, that particular body. So we'll just see the quick video here, and then we'll get more detail about the Archimedes law, and how it is also applied in today's date as well. So all these are very relevant in today's date. So here if you just see, so this is a small or beaker, and if we have all experienced that, it is nothing to demonstrate or nothing great here, but you see the observation. They are observing when they are putting some object, some finger or hand, so water is coming out because hand is occupying that space. The volume of hand will be also displaced by that amount of water. So Archimedes exactly observed the same thing when he felt that in a bathtub. So now how he came to this conclusion that amount of water, weight of that particular water will be equal to the upward force. So when you dip this particular object, I'm sorry, when you dip this particular object, so here, see, bound force applied by the fluid is equal to that. So now you just take a minute and understand what they are doing. You see, this is a 5 kg weight they are measuring, and you have also experienced when you see in the bathtub or in the swimming pool, you will feel like something lighter. The same thing we are measuring here. The same 5 kg, if you dip here, so it will, you see the measurement is coming somewhere 2 kgs, and the water will of course come out because this particular object is occupying that space, and water will come out. So this is the displaced water, what you see on the right hand side. Now this weight of this water, displaced water, will be the force applied to this particular object. So this is what is Archimedes law or Archimedes principle is all about. And using this law, this principle, we can understand. So coming back to our story, so or you just see this one. See here, using this law, if you see that big vessel, submarines, or anything is floating using this law, because the amount of water it is displaced by this particular object is that amount of force applied to that particular object. So this is the conclusion. So hope you understood Archimedes law. So I'll just take say few minutes here. I'm just coming to the main conclusion of this one. So here see now floatation, how one object floats. So using that particular principle, see now if we see that amount of weight is greater in the figure A, if you see that amount of weight is greater than the amount of force applied on that particular object, then of course that body will sink. Now if you see that amount of weight and the force is equal, then that body will float. And if you see that amount of force is more than that weight, so it will float very comfortably. Okay, so where from this is coming, I'll just take, I'm sorry, I should use that board actually. See, if you derive this one, mg means what? Mg means it is volume into density. So student, are you with me? Mg means what? It is volume into density. I'm just coming to the main equation here. M means what? Volume into density. Are you with me? So weight means M into G. Yes, tell me.
Sir,
He said yes. Yeah.
Okay, thank you. So volume into density. Now, how that story is now coming into my mathematics. Mathematical equation, M means volume into density. We all know that. Okay. Now, the more you increase the volume, see, the volume, more you increase the volume, the mass will be more. See, now, if you make a ship, the base of the ship is the iron. We all know that. It's a heavy material. Now, if you flat it, if you increase the volume, okay, now, here the amount of water will be displaced by that volume is more. See, this is the mass of that water displaced when we are dipping that particular object. Now, if you make the volume high, M will be high. Density is constant for that any material. We all know that density is constant. Okay. Now, we cannot change the density. We all know that. We have seen in our first assumption, we told two assumptions we took. Incompressible, density of the liquid independent of the pressure. Okay, so now if density is constant, if we increase m equal to v into rho, it's a simple mathematics, but try to get the essence of this simple formula. If I increase the volume, if I flatten my metal object, the iron plate, then amount of water displaced by that metal will be more, because volume is more, density is constant. If v is more, m will be more. If m is more, then the buoyancy will be more, because buoyancy is nothing but m into g. G is constant for that particular place. If we are doing in the earth, it is constant. If we go in space or moon, it will be different. But we are not getting into that consideration right now. What I am saying, if I flatten, say v is in my hand, I can make that shape of the ship as I want, and that's what exactly is there in submarine, in big ship, in small object, big object. So if I increase v, the amount of displaced water will be more, because m will be more. If m is more, that upward buoyancy, upward force, what we see here, it will be more, because amount of water by that particular big volume is displacing more water. So more water means m is more. M is more means my v will be more. That means if I flatten that surface, then I will be able to get more buoyancy from the water, and therefore the vessel is floating. But iron block cannot float. Okay, and therefore exactly the same thing what this equation shows. These are very, very simple equation, but try to get the essence. So if I have to make m bigger, see mg greater than this one, if I have to make m bigger, I have to increase the volume. M equals to v into rho. We have seen that rho is constant. So I have to make v large to make m large. Okay, and therefore we can make that object floating. Another important concept is there, coming to that story once again. So every time I tell the story and go to other topic, story here says that Archimedes told king, you make a same crown with a real metal, with no impurities. Okay, now no impurities, same volume, no impurities, same volume, another object of the crown, another crown actually, object here is the crown, the king made, and Archimedes dip into the water, both the real and the fake one. Fake means it has some impurity. Then the volume is same, everything is same, but the metal has a different density. Wood has a different density, iron has a different density. Real gold has a different density, with impurity it has a different density. Okay, when they dip into the water, the amount of water displaced by the real object and the mixed object will be different, and due to that difference, Archimedes exactly pointed out how much impurities was there. So this is a very simple thing. There are lots of things are there, so I just thought of explaining you. So this is what it is. Another point is there, maybe in my next class I'll explain how we can derive Newtonian motion from Archimedes principle. So you read this one, maybe in the next class. So Ujjal sir, I just take this to the next class just to touch upon this one, because I see students are waiting for a long time, so I do not want to extend more. So here I'll just conclude what we have studied, and last part is that is also important from problem solving point of view, how we can derive, say, Archimedes law from Newtonian physics. So that part we'll discuss in our next class. So due to the time constraint, we'll do that. So just to summarize what we have seen from the beginning, we have seen that fellow is breaking a brick on the chest of that fellow lying on that needle bed, and we have seen the pressure force by area. So amount of force you apply doesn't matter. I can minimize the pressure if I increase the area. And Pascal is that unit of that pressure, it is Newton per meter square. But when it comes to the fluid pressure, we have seen area doesn't matter. What matters? Height, density, and the gravitational acceleration. Okay, and we have seen in the next video or next explanation, Boyle's law, that pressure and the volume is constant. P1 V1 equals to P2 V2. Just remember P1 V1 equals to P2 V2. Pressure and lot of problems you can solve using that. Now coming to the Pascal law, what we have seen, that F2 equals to F1 by A1 into A2 means what it does, the F1 by A1 is the pressure that is applied in a small cylinder, and that same pressure goes everywhere without changing its magnitude. And when it goes in anywhere, and if I increase the area, the amount of force will be more. And that is exactly what we have seen in our hydraulic brake, in our hydraulic press, or so many other examples are there in the book. You can see that. Now coming to Archimedes principle, that upward force equal to weight of the displaced liquid. Just remember this. Always you relate to this mathematical equation, it will be very easy to remember the entire all these jargons of English and all these things. Even if you forget those jargons, if you remember these mathematics, you can also write that particular English, particular things in the examination if you forget that also. But if you remember upward force equal to weight of the displaced liquid, that's it, you are done. So you remember Pascal law means you remember F2 equals to F1 by A1 is the particular pressure into by area it is coming. You remember P1 V1 equals to P2 V2, that's it, you are done with the Boyle's law. Okay, P equal to H rho G, you remember that mathematical equation, that's it, you are done. So fluid pressure depends on rho, depends on depth, and depends on that small g, that's it, you are done. So buoyancy equals to mg, what Archimedes is saying, P equals to mg. So this is the takeaway from this session today. So any questions, anything, please feel free. I know I took long time, so 1.5 hours I took. So once again, thank you for your patience. So I'll just stop sharing this screen, and maybe I can take questions. Feel free to ask anything. Yeah.
A great session, sir. Means I listened to the entire thing, and it is really a great session. I really appreciate, sir. Good. I think students, please feel free to ask questions if you have any, or if you want to ask questions later, that is perfectly fine. And as sir has told that at the Konark classes online platform, you will get the relevant questions. We will solve these questions together. Okay. Perfect. I think we can conclude the class here, sir.
Yeah. Thank you once again. Thank you, and I am sorry for those technical difficulties. But feel free to solve Konark classes questions. That will help you to understand the theory better. So that is the conclusion. And please go ahead, study well. And any questions, anything, Konark sir is there. We all are here. We'll help you to achieve your goal, your target.
And we'll announce the next class of the next session. We'll announce shortly.
Sure.
All right.
Thank you. Thank you all. Bye.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you.